Okay, a couple of announcements. Homework 8 is due on Friday of this week. And then next Wednesday, we're going to do the wastewater treatment plant tour. And I've been in touch with them to confirm. And they mentioned that there's limited parking available. So we can't, each one of us, take our own personal vehicle over there. We're going to need to carpool. So I've got a sign-up sheet, and I'd like you to put your name on one of 3 pages. The first page is what I'm calling the solo driver for someone who maybe lives on that side of town. The treatment plant's over by Camden Park. So like if you needed to go immediately home to Kentucky after the treatment plant tour and you're not coming back to campus and you're going to drive yourself, put your name on the solo driver. So that's if you have to drive yourself to the treatment plant and you can't carpool if you're not able to drive anyone. Hopefully that's a short list. The second page is flexible driver. So that's if you have a car, you're willing to drive if needed, but then you might end up being a passenger depending on how many people are flexible drivers. Put in parentheses the number of people that you could drive if you're able to drive. And then the third page should be people who would just want to be a passenger. So either they can't drive, they don't want to drive to the treatment plant. So does everybody understand the essence of these 3 pages? So your name should be on one of the 3 pages for the treatment plant. Start that circulating around. So the next assignment after that, after number 8, is homework 9. That's due on Wednesday of next week. This is a big assignment, homework 9. I think that, it would be worth taking an early look at. So a couple of the questions require you to set things up in Excel. And, the first time you're setting up these types of problems in Excel, it takes a little bit of time. So I just wanted to acknowledge that homework 9 is a little bit bigger. It's a larger than average assignment. Then one other announcement is that we will also be visiting a water treatment plant in April. So it's the West Virginia American Water has agreed to host us here in Huntington. More details about that, but we're going to start by going to the wastewater treatment plant, and we'll go to the water treatment plant in April. So does anybody have any questions about the announcements?
I have a question on the last homework.
Mm-hmm.
Number 7, I think. The first question, it was like just estimate the size of the filter. And
which assignment? You're talking about homework 7?
yes.
Okay, and what's your question?
Well, I estimated it and somehow I got it wrong.
Okay. Because
it's okay. It's like no big deal. But
yeah, maybe we've got some time at the end of class to go over that.
Okay.
But I wouldn't want to go too deep on that at the expense of preparing you for the next assignment.
Okay.
So, you and I can go over it together in my office during office hours, or if we've got some extra time at the end of the class, then we can talk about homework number 7.
Okay.
Any questions related to the announcements? Okay. So in homework 8, I just wanted to point out that there's a question about differentiating between the suspended solids and the dissolved solids. And so what's happening is that water is being filtered across a plastic membrane, and anything that is solid that's suspended will be captured on that membrane. And so where you're doing the before and after weight of the membrane, that tells you how much of the suspended solids there were. And then when it comes to what passes through the membrane, if there's any solids that accumulate in the bottle below the membrane, then that's associated with dissolved solids. And then one other thing is that in the homework you'll notice this symbology BOD subscript 5. What that means is the BOD that has been exerted after a period of 5 days. And so sometimes it's common in analysis of wastewater to test either the 3-day or the 5-day BOD. And so BOD 5 just means that the time of the BOD is 5 days. And you'll need that for one of the problem-solving questions. All right. So This is where we left off on a prior in-class exercise. We were going to do the graphical determination of the BOD rate constant. And let me remind you what that one looks like. So we had already solved the first part of the in-class exercise related to BOD. For example, finding the rate constant from the 8-day and the ultimate BOD, knowing what the K values are. But this is the problem that we hadn't got to yet. And it's a graphical procedure that you need to know how to do for the homework. It's basically learning how to determine the rate constant and the ultimate BOD when you don't want to do a 30-day long test. So you can see what we have is data that goes through 8 days of data. And we can see how much BOD has been exerted over an 8-day process. But we want to know terminally, if we were going to allow bacteria to break down all of this substrate, how much oxygen would they demand? And so the first step of that is just to come up with T divided by BOD to the 1/3 power. So obviously it's going to be 0 for this first one. For the next one, T is 1, BOD is 32. So T divided by BOD would be 1 divided by 32 to the power of 1/3. So let me pause for a moment and have you fill in the remainder of this table, and then I'll show you how we're going to take that and graph it on the back side of the paper. So just calculate T divided by BOD for days 1, 2, 4, 6, and 8. When you've got the data, flip the paper over and graph it on the back side. So we've got time in days. Just put the data point. So for example, let me see if I can drop the data points on here. It's sometimes not very easy to draw using Word, but there's a data point here at day 1 and 0.315. So I put that here is a data point. Day 2, 327. Day 4, 362. Day 6, 384. All right, so if you've got the data points graphed, then the next thing we'll want to do is put in a best fit line, including we want the best fit line to go through the intercept. So let me just draw a line here, kind of trying to make sure that these are all along the same figure, all along the same trajectory here. Sometimes it's going to be a little bit above, sometimes it's going to be a little bit below. 362, maybe I had that one a little bit higher, 362. So what we want to do is identify, as you can see in the instructions here, what is the intercept. So, you know, my impression of the intercept is that it's maybe like 0.301. So I'm going to say A is 0.301. And then I also want to know what's the slope of the line. Here it says that the slope of the line is B. And so the slope will be the rise divided by the run. So here, maybe the easiest place to see the slope is, see how it's crossing here on day 7? It's crossing 0.4. So that would be a convenient place for us to determine the slope. And also at day 2, you notice how it's crossing 0.33 at day 2? So at day 7, I'm going to say, so the rise is, day 7 is associated with 0.4. So 0.40 minus, over here, day 2 is 0.033. 0.33. That is the rise. And then the run is 7 minus 2. 7 minus 2. So the slope is 0.07 divided by 5. So the slope is 0.014. And that's B. So B is 0.014. And what the Thomas graphical method says is that the rate constant and the ultimate BOD can be determined by looking at a few days worth of data. And so L naught, the ultimate BOD of this wastewater, is going to be 1 divided by 6 times A squared times B. So 1 divided by 6 times A is 0.301, which will square, and then multiply that by the slope, which is B, 0.014. All right, so if you'll get your calculator and follow along, what's our ultimate BOD going to be here? 1 divided by 6 times 0.301 squared times 0.014. Okay, I get 131.4 milligrams per liter. That is the ultimate BOD. And this is a good time for us to just do a quick reasonableness check. You know, if it's 1,000,000, maybe that would tell us that we've gone astray. Or if it's a value that's less than the BOD we've already seen exerted, that would also be an indicator that something's not quite right. What this is saying is that the BOD is eventually, it's in that kind of tapering off phase where with each additional day, it's progressively less and less BOD that's being exerted. Look, in the first day it was 32. In the second day it went up a little bit more, but less than it did in the first day. So it's kind of already gradually becoming a plateau, but this is just suggesting that if we used up all of the BOD, it would end at 131.4 milligrams per liter. The last thing that this is showing is the slope. Using the slope and the intercept to determine the K value, the rate constant for BOD. So 6 times B, so K is 6B divided by A. Okay, so 6 times 0.014 divided by 0.301. And so the rate constant here is going to be 0.279 days to the minus 1. That's the K value. Let me bring all this up on the screen. I think I've got graphical solution. All right, so just kind of showing those data points, the best fit line from which we want to get the slope, and also the intercept, and then we can get the K value and the ultimate BOD. This is the Thomas graphical method, and I think that you've got a homework problem where you're asked to do this same procedure. Anybody have questions on how to do that? Okay, now remember, BOD is a consequence of adding a substrate to a natural water that will have bacteria. So the effect that it has, that we care about most, is this dissolved oxygen sag. It's the effect of the substrate, which is that the bacteria are simultaneously consuming food and breathing oxygen, breathing dissolved oxygen, that we're concerned about. So there's a model that allows us to predict the depletion of dissolved oxygen in a river. And it starts off by assessing how much of a deficit there is in dissolved oxygen. The deficit being the difference between saturation, which is the maximum amount of dissolved oxygen there could be at a given temperature, and the actual concentration. So the deficit is, looking at this figure, the dissolved oxygen should be, let's say, 8 milligrams per liter. And so the deficit is just how far below that line of 8 milligrams per liter we are at any given point. So it looks like at this lowest point where it's saying 2 ppm, the deficit would be 6 ppm. If we're starting off at the initial concentration being 8 and it's sagged down to 2, deficit is how far away we are from saturation. Now remember, we talked previously about how the air gets back into the water through a very slow process. The reoxygenation process depends on the temperature of the water. It depends on how quickly the water is moving and whether it's experiencing rapids, which would increase the rate of reoxygenation, or if it's a slow-moving, stagnant water, which is going to have less diffusion of oxygen from the atmosphere. But what we want to do is develop a model that allows us to calculate what is the dissolved oxygen concentration at any location. And we do it by determining the deficit and looking at the difference between the rate of oxygen consumption and the rate of oxygen re-entry into solution. So in river dissolved oxygen, we're going to be modeling the effect of BOD by comparing these two different rates. The deoxygenation rate constant, which is related to the microbial activity, and then the reoxygenation rate constant, which is related to river hydraulics. It's related to river hydraulics and also, for example, like the temperature of the water. So we'll have a sag, and depending on how we arrange this model, we can either use it to calculate the deficit at any given point and therefore the dissolved oxygen concentration, or sometimes we just are focused only on the critical point. We want to know how bad is it going to get. And so there's a separate equation that will allow us to calculate how long, in terms of time, travel time, it takes to get to that critical point. Because if you know where the dissolved oxygen is going to be the lowest and how long it takes to get to that point, then everywhere else is a little bit less important than that low critical point. And normally you'd have some sort of a standard or criteria saying that you're not allowed downstream to go below a certain dissolved oxygen concentration. So being able just to calculate what is the DO at the critical point and being able to pinpoint the location on the map to go out and measure the critical point, it's a valuable thing to be able to predict with this numerical model. And so the numerical model uses an oxygen balance model. And what you're looking at is, this mass balance approach says that you look at the flow in and out of some constituent plus the net rate of reaction. And we are going to have oxygen consumed in the water. So if we're doing a control volume, just saying like take a certain parcel of water that's flowing downstream. So if we had a volume of water that was 1 cubic meter and we were tracking the movement of that 1 cubic meter of water downstream, then the amount of oxygen in that cubic meter of water is going to be changing depending on what rate the bacteria are consuming oxygen, and then the net difference between inflow and outflow across the river surface. And so in our case, it would be inflow. Anytime the oxygen concentration goes lower than saturation, then oxygen is going to start going into the water. So the outflow term, like rate of oxygen out, is negligible, and there generally won't be a significant amount of oxygen produced in the water unless it's got a lot of algae. Algae can produce oxygen in the water, but oftentimes we'd neglect any effect of algae, especially because algae is more prevalent in lakes, less so in rivers under most circumstances. And so the worst case scenario would be that we don't have algae producing any oxygen as the water's flowing downstream. So what it comes down to is just looking at those two terms that do kind of dominate. If there's no production of oxygen due to algae, and if there is no oxygen flowing out because the water's already below saturation in the atmosphere, there's only inflow, the change in concentration of dissolved oxygen over time is the difference between the rate in and the rate out. And so our model is going to estimate these two rates depending on empirical factors like the waste characteristics, depending on the temperature of the water. So remember that both of these are going to be first order reactions. The bacteria act more quickly when there's a high concentration of food. The rate of reaeration is faster when there's a larger difference between saturation and the actual concentration. So both of them are dependent on the concentration of the constituent that we're modeling, whether it's bacteria amount or the water that's containing oxygen. So deoxygenation is dependent on biological activity, and the rate of the deoxygenation depends on the difference between the ultimate BOD and the BOD at a given time. So that's the driving force. Remember, it's first order kinetics, and first order kinetics is asking some sort of a question about amount. And the amount that matters is how much BOD remains to be consumed. So at the start of a reaction, when no BOD has been exerted yet, then the ultimate BOD, it's going to stay constant. But if there's no BOD that's consumed yet, when we first dump the waste into the river, then the deoxygenation rate is going to be at its highest. But then the deoxygenation slows down as the difference between the ultimate BOD and the BOD exerted at a given time is decreasing. So what's in the parentheses here is the driving force. And the reoxygenation rate, the driving force, is the difference between the concentration of oxygen at saturation and what is your actual concentration. So if you have water with very little oxygen in it, then the rate of reaeration through diffusion is much faster than if you're almost already at saturation, then there's less of a driving force. The oxygen doesn't diffuse into the water when it's almost already at saturation. It doesn't diffuse very quickly. Okay, so there's an empirical formula in your book. It's equation, I think, 733, that allows you to estimate the deoxygenation rate based on lab data. So this K value here would be based on if you just did a bottle test. But how do bacteria behave in the real world is different from how bacteria behave in the bottle test. And so this overall equation is saying that the deoxygenation partly depends on the bacterial kinetics that we can assess through a bottle test, but then it also depends on the river characteristics. The velocity relative to the depth of the water, h, and then a bed activity coefficient, which varies from about 0.1 to 0.6. It's kind of, you can think of it as like, are there rapids in the stream? How is that affecting the deoxygenation? Now the reoxygenation rate, you can see, is also a function of the river characteristics. So like the stream velocity, the depth of the water, and the temperature. In the next homework assignment that's due on Wednesday of next week, I give you an equation that allows you to estimate the velocity of flow. It's called Manning's equation. And so there's kind of a two-part calculation to determine the reoxygenation rate, because you have to know how fast the velocity of the water is moving, which you can determine from Manning's equation, which is on the assignment handout. And then you'd use this formula to determine how quickly the oxygen is getting back into the river, depending on the flow characteristics. So we're going to do an example that uses all of this, but our book has some empirical reoxygenation constants. Like, we can calculate it or estimate it based on the flow conditions, but there's also a table in your book that just says, for example, if you've got small backwaters, meaning a small stream that isn't moving very quickly, then the reoxygenation constant is going to be really low. Whereas the faster moving the water is, the higher the reoxygenation constant is. And this is assuming 20 degrees Celsius. And, you know, what's a swift stream? That's a little bit vague. So it's nice if you can to use this formula to calculate the reoxygenation rate. The Streeter-Phelps method is what allows us to predict the oxygen deficit as a function of time. And if we know the deficit, then we can determine the oxygen concentration. Because remember, the concentration would just be saturation minus the deficit. So here's the formula. It's predicting the deficit at a certain time, and by time, what we mean is we're probably going to calculate that in days, because most of the time our K values will be expressed in units of inverse days. And so we would say, maybe half a day downstream. If the water's flowing downstream from some discharge a certain amount of time, this is going to tell us what would be the deficit in the oxygen based on the difference between the re-aeration and the de-aeration. So it's the rate that the oxygen is getting back into the water versus the rate that it's being used by the bacteria. You can see one of the terms here has to do with the ultimate BOD. But then this separate term here is also taking into account the fact that sometimes the oxygen could be at a deficit even before we add the waste. So, we don't assume that immediately prior to the discharge that the water was perfectly saturated with oxygen to begin with. So this is the first part of the Streeter-Phelps equation. You use it to predict deficit as a function of time. We can rearrange that equation and just focus exclusively on the worst case scenario, which is the lowest point in the sag, where the deficit will be the greatest. And so the Streeter-Phelps method also can be used to predict how much time it will take to get to that point of maximum deficit. And it just looks at the difference between the re-aeration and the de-aeration. And so it's kind of taking into account the initial deficit, the ultimate BOD, and predicting in time terms how far downstream you're going to see that maximum sag. All right, this all probably seems pretty abstract, and I think it'll become more accessible if we actually put it into practice. So let's do an example and say we've got a river that we're interested to model, and we're going to use the Streeter-Phelps method to predict how far downstream is the point of lowest dissolved oxygen and what is the dissolved oxygen at that point. So we're going to use the Streeter-Phelps method to do this, and so here's a diagram just to illustrate. The river is 3 cubic meters per second. It's got an initial temperature of 5 degrees Celsius. The initial amount of BOD that's in the water is very low. There's only 1 milligram per liter of BOD, ultimate BOD, prior to some discharge coming in. And initially, the dissolved oxygen concentration is 7 milligrams per liter. I'm going to give you a handout that has the saturation table. So what you'll notice is that at 5 degrees Celsius, the saturation is 12.75 milligrams per liter. So there's already some deficit before we add the stream from this factory. So we've got a factory that we don't know what it's making, but they're discharging wastewater into the river, and what they're putting in there is a flow rate of 32,400 liters per minute. It's warm water. It's got a high ultimate BOD and even lower dissolved oxygen. So we're going to use the Streeter-Phelps method and these known characteristics of the river's cross-section, the deoxygenation and reaeration constants. And here's the model to predict what is the time to the lowest point downstream, and then also what is the deficit at that location, and then therefore what's the dissolved oxygen at that location. Now the handout I'm going to give you takes you through it step by step. Let me give you the papers. Okay, so the handout I've just given you, you can see that what I'm suggesting you do first of all is temperature balance on the river. And hopefully you remember a mass balance that we've done. Now strictly speaking, temperature is not conservative when you are mixing streams, but you can get close enough for an example of this accuracy. But if you've taken thermodynamics before, maybe you'd know that you can't balance temperature in the way that we're going to, but it's pretty close. So for part one, let's do this first one together, and then I think you can get the idea and do the other ones on your own. So the model is that the temperature of stream 1 multiplied by the flow rate of stream 1 plus the temperature 2 times Q2 is equal to T3 Q3. We've done stuff like this before with concentration. Remember, we've done river mixing where the mass in and equals the mass out. So we're assuming here that the heat in equals the heat out. So T1 is 5 degrees of the river. So 5 degrees Celsius is the first river, which flows at 3 cubic meters per second. And T2 is 35 degrees Celsius, which is flowing at a rate of 32,400 liters per minute. Okay, well we need to convert that, by the way, to cubic meters per second. So 32,400 liters per minute, well that's the same as 32.4 cubic meters per minute, which if we divide by 60 seconds per minute, the Q2 is going to be 0.54 cubic meters per second. Okay, so let's use that as Q2. 0.54 cubic meters per second is equal to T3, which we don't know. T3 is the unknown, times Q3. Q3 is just going to be Q1 plus Q2, so 3.54 cubic meters per second. Okay, so T3 is 5 times 3, 15, plus 35 times 0.54. Let me get my calculator. I can't do that one in my head. 35 times 0.54. 18.9 divided by 3.54. So the temperature of the mixture will be 9.57. So 9.57 degrees Celsius. So let's use 10 degrees Celsius because our table is in 1 degree Celsius increments. So we're mixing cold water and warm water together, and we get lukewarm water coming out of it. Okay, so that's what you did for part 1. Let me bring this up on the screen just for somebody who might be following this at home. So part B, do the same thing, mass balance for the dissolved oxygen concentration of the mixed water. So we started off with 7 in the stream 1, 1.1 in stream 2. Use the same mass balance and mixing model to predict what's the concentration of the mixed water after the 2 streams have mixed. And then also do the BOD concentration of the mixed water. So mass balance on those 2 things, part 2 and part 3. Okay, so we did the temperature mixing and got about 10 degrees Celsius. If you do the, what's the dissolved oxygen concentration in the mixture, I think you should get about 6.1 milligrams per liter. And then the BOD concentration of the mixture is 8.47 milligrams per liter. So it's a weighted average is what it is. You know, like this mixing model is just a way of saying that if you have a high flow rate but a low concentration of BOD, and then a high concentration of BOD but in a lower flow rate, then the average concentration after the 2 mix, it's not just a simple average. You know, you wouldn't add 1 plus 50 and divide by 2 to find the concentration of the mixture. The concentration of the mixture depends on how much there is of each of the 2 streams that are being mixed together. Okay, so that is that's how we've got so far the concentration of the mixed water and the BOD of the mixed water. Now the next thing, what's the initial deficit of oxygen? So remember, deficit is the saturation concentration minus the actual concentration. So we got that the DO concentration is 6.1 milligrams per liter. So in the table, we need to find out what's the saturation concentration at 10 Celsius, because that's the temperature of the mixture. So 10 Celsius, the saturation concentration S is 11.27. So therefore deficit, the initial deficit, meaning just after mixing, just after the 2 streams come together, saturation is 11.27 milligrams per liter, and then the actual dissolved oxygen concentration that we've calculated so far was 6.1 milligrams per liter. So the initial deficit is 5.17 milligrams per liter. Does anybody have any questions about the terminology we're using? Because, I mean, there's a lot of new things here that we're talking about, like ultimate BOD, deficit, initial deficit. Anybody have any conceptual questions that they need to have clarified before we continue? Okay, the heavy lifting starts on page 2. This is where we're actually going to start substituting things into the model. So I'd like to have you calculate what is the time to the critical point to where the dissolved oxygen is going to be the lowest. So we know from the first page of the handout that the KR is 0.75 inverse days and KD is 0.53. The initial deficit, D naught, the initial deficit we just calculated to be 5.17, so that's D naught. Initial ultimate BOD, L, we calculated that to be 8.47. So just substitute all those values into this and find out how many days downstream is it that we get to the point of the lowest dissolved oxygen concentration. For the homework, you're going to have to type this formula into Excel, the Streeter-Phelps formula. So what I recommend you do before doing the homework assignment is try setting up this example problem in Excel, so that you are confident you've got the equation typed in correctly. If you use some given numbers that you already know the answer to, then that would help you to feel confident that you've got a working formula in Excel. So for example here, our time to the critical point where the DO is going to be the lowest is 0.25 days. And then in terms of the distance downstream, we would have to know what's the velocity of the flow. And so the velocity of the flow is the flow rate Q, 3.54 cubic meters per second, divided by the cross-sectional area that was given in the problem statement, where it said that the river's cross-sectional area is 11.4 meters. So that tells us that the speed of the water, its average speed is 0.31 meters per second. So if it's flowing 0.31 meters per second for a quarter of a day, so that's 6 hours, and we have to know how many seconds are in 6 hours. It turns out it would travel about 6.7 kilometers during that time. And if that's the location of the critical point, then we can also use this Streeter-Phelps method to predict what is the deficit at that location. And so the deficit at that location, again, we're dealing with exponents, and the way that you do the exponent in Excel, by the way, is the exp function. So e to the power of negative k times t would be exp, and then in parentheses minus kd times the time. So the deficit in our example at that location 6.7 kilometers downstream, the deficit is 5.24 milligrams per liter. And so therefore, if we know what the saturation concentration should be, 11.27, and we know what the deficit is, then we can predict what is the dissolved oxygen concentration at that location. It'll be 6.03 milligrams per liter is the lowest it's going to get. That's the worst case scenario. And in the homework, I ask you, how much waste could you discharge and have the dissolved oxygen stay above a certain threshold? And so the nice thing about Excel is that once you've got it set up, you could, for example, just keep increasing the flow rate Q of pollution trading enterprises and then see how does that affect the dissolved oxygen concentration. So that is, all of that's on the assignment that's due on Wednesday. So here's what I'm going to do. I'm going to demonstrate in a video that I record in my office, and I'll send you a link to, how to set this up in Excel, because I recognize that maybe some of you haven't become power users of Excel yet. So I'll just set up this example in Excel, encourage you to do the same thing so that you've got your own working model. And then I think once you've got this working in Excel, you'll be able to adapt it for the homework pretty easily. So look for an email from me once I get a chance to record that demo video and load it onto YouTube. And hopefully that will be just like a further resource as you solve the homework assignment. I've kept you 1 minute late. I owe you a minute, so I'll let you out early on Friday.